So let's just try some of these ones here. So if you look at this first one here, we have our integral symbol coming out front, and then the dx out in the back. And so the part that we're enclosed in that is going to be then the x to the fourth plus 3x minus 9. And all we need to do for this one here is take the antiderivative for this one. For each of those three terms, we can do each term independently, and we'll just use the power rule then for each of those. So the first one then, I'll add 1 to my exponent, and I'll end up with then 1 over 5, x to the 5, plus 3 over 2, x to the 2, minus 9x, and then plus c. And that's all there is to it. You're just going to take the antiderivative of each of the terms. Now the one over here is going to be essentially the same function, but what we'll notice for this one here is only the x to the fourth and the 3x are between the integral sign and the differential. And so only those two terms then are going to be taking the antiderivative of, and then the 9 is outside of that. Now we're not really going to be dealing with this type at all, but just to give you an idea of what's going on with that integral and the differential, for all the ones we're going to be doing, all the terms will just be between those, but this is also a valid way of solving some of those, and as you go on in calculus, you'll see some of those. So in this case here, what we'll see then is we'll get that same, the 1/5 x to the 5 for the first term. We'll also get then the 3/2 x squared, because those two are in the differential. We'll get the plus c, and then the minus 9 is outside of the differential, so we're not going to be taking that. Again, we only take the antiderivative, the things in between the antiderivative sign and the differential. Our next cases then are going to be then the definite integrals, and so we'll scroll down to these ones here. And so we'll still be taking the antiderivative as before of the piece in between the integral sign and the differential, so the x squared and the 1, but now we'll be applying then the 2 and the 0 then to that antiderivative. So our first step is going to be the same. We'll take the antiderivative between there. So again, we can use the power rule for this one here. So we'll get 1/3 x cubed and then plus x. Now with the definite integrals, we don't need to include the plus c. It's going to cancel out when we do the subtraction, and so really we're never going to place that out. Now we are going to move our limits of integration out to the back here, and it's just a straight line or kind of a large bracket, and that's just going to indicate we've already taken the antiderivative, and now we just need to apply this, and we can do that in our next step. And so when we do this, we'll take then our 1/3, we apply our upper bound first, so we have 2 cubed, and then plus 2. Now I would recommend always using a large bracket for this. Now in this case it is just going to be 0, so that wouldn't matter, but that negative does need to go through to every term, so you do want to be careful with that. And so then we'll end up with that just the 8/3 plus the 2, which will give us then 14/3. If we jump to this one here, now we'll see that we don't have to end at 0 or even a positive number. We can go across the x-axis into the negative ones here. And so we'll take that 3x minus x squared. We'll take the derivative then of that. And so then we'll have the 3 over 2 x squared minus 1/3 x cubed. And then we'll solve that then between the 5 and the negative 1. So we'll take 3/2 5 squared minus 1/3 times 5 cubed. And then we'll subtract. Now again, we'll want to use that large bracket because both terms will want to subtract. So we'll get then 3/2 times negative 1 squared, and then minus 1/3 times negative 1 cubed. And close that with the large bracket, and then just a matter of solving that piece here. And if you solve that piece, then you'll end up with a negative 6. So we can check these ones on our graphing calculator. So if we look at this one that we've done here, the 3x minus x squared, I've just gone into my y equals there and put it in then for my y1. So I'll go ahead and graph that. And we'll get then, of course, a parabola for this one here. Then I'll go second function trace. And I'm going to go down to number 7 here, which is the integral then of f of x dx. So we'll take then that. It's going to ask for a lower limit, which was -1. Then it'll ask for our upper limit, which of course was 5. We'll hit enter, and we'll see which parts it shades then. And so again, always between the curve and the x-axis. So this region here is going to solve as a negative. This region will solve as a positive, and then this region again as a negative. And we see then our answer gives us the limits below, -1 to 5. And then the integral then is equal to -6, which is then the integral then of that function over that particular domain. All right, so if you go back to then the back page, you'll see 4 more. And so I'm just going to encourage you to just pause the video here and give these 4 a try, and then restart the video and see how you did. So for this one here, I'm going to take the antiderivative of the 3 root x and the negative cosecant cotan. I can split that one up into 2 separate integrals, and that'll make that a little bit easier. So I can take the integral of 3, and I'll put this into exponent notation. I'll close that one up, and then I'll subtract from that then the integral of cosecant x, cotan x. And again, we'll see that we have then that differential on the end of each of those one there. So we will put that differential to close out the 3x to the 1/2, and then the cosecant cotan. Again, all the differential is doing is just enclosing what we're taking the integral of, and so if we're splitting it up into 2, we'll again carry 2 integral signs and 2 differentials. So for our first one here, we'll add 1. That'll give us 3/2, and so we'll have 3 over 3/2, which will just be 6 over 3, and that'll give us then x to the 3/2. I've taken the antiderivative, so my dx is going to go away as well. Now if you look on your formula sheet, the derivative or antiderivative of cosecant cotan is just going to be negative cosecant. And so I'll get a negative, and a positive. Now this is an indefinite integral, so of course we'll have the plus c there as well. So we can clean that one up a little bit. Again, just change that complex fraction. And so that'll give us 6 over 3, or just 2. 2 to then the 3/2, and then plus, now because I have the 2 negatives, cosecant x, and then always that plus c for the indefinite integrals. So this will be a definite integral with pi over 4 and 0. So this one here is going to be secant squared. Now if you look on your formula sheet, the antiderivative of secant squared is going to be tan. And so this one then is just going to equal then tan of x. And then we'll solve for that then between pi over 4 and 0. And so we just need to take then tan of pi over 4 minus tan of 0. And of course, pi over 4 is 1, or tan of pi over 4 is 1, tan of 0 is 0, and so this one is just going to equal 1. We're going to find it's a little bit easier to change the form of the equation before we take the antiderivative. And so for this first one here, whenever you see an antiderivative that has that numerator and then just a monomial term in the denominator, I'd recommend always splitting it up between the two. That's true for derivatives and for integrals. If I take the 3x cubed over x squared and then the 5x over x squared and treat it as 2 separate terms, and that's just going to make my life a little bit easier here. So I'll split this one up. I have 3x cubed over x squared. Close that one up with a dx. And then minus the integral of 5x over x squared dx. So it'll give me that second term there. So this one here then, I can simplify that one further. It'll just give me 3x dx. That's a very easy integral or antiderivative to take. And then this one here will just give me then 5 over x, which then also then the dx. So for the 3x, I can just use the power rule for that one. It's going to give me 3 over 2 x squared, and then we'll finish that one off. Now this one here, I have the x to the negative 1, but if you remember, that's the one you can't use the power rule for, but that's just going to be then the natural log. So the derivative of 1 over x is equal to the natural log, so this one just becomes 5 natural log of x, and then of course plus c because it's an indefinite integral. What I'm going to do for this last one, we're going to change the form again for this. So we'll multiply through this bracket and just change that into a quadratic with 3 terms, and then we can apply the derivative then, or the antiderivative to each of those individual terms. So we're going to have then 4 to 0, and I'll just multiply this one out. So 7 times 7 is going to give me 49. I'll get then negative 28x as my middle term. And then my last term then is going to be plus 4x squared. And then we can close it off with dx. And now we have a much easier integral then to take. So I can take then the integral of each of those terms independently of the other ones. So 49x minus then 28 over 2. That'll give me then x squared. And then this will give me 4/3 x cubed. And then I'll be solving that between 4 and 0. And again, I don't need to put the plus c with the definite integrals, just because it always cancels out. So we can put our values in for 4 and 0. And so I'll get 49 times 4. The 28 over 2 is just 14. So I'll get 14 times 4 squared. And then plus 4/3 times 4 cubed. Now I'll subtract then. Now I won't sub in that for 0 all the time, but we can see this goes to 0, this goes to 0. So what I'll be end up subtracting then is just 0 for all those terms. So we'll just simplify that one a little bit. And then when you solve that, you'll get 172 over 3.